Hello everyone, and welcome back to another tutorial video focusing on the problems that were on your homework set number 4. In this video, I'm going to go over the problems that I assigned from section 2.2. Those are the problems focusing on critical points and on their stability. Now, as usual, I like to begin these tutorial videos by doing a quick recall of the concepts involved. And in this case, we have the idea of a critical point. A critical point, at least whenever used in any sort of calculus context, basically means mathematically a point where the function is flat. In other words, where the derivative is 0. Now, if you have a differential equation, which will usually have the format, say, dy dx is equal to some function of the variables x and y, then finding critical points is pretty straightforward. It just amounts to solving f of x comma y equals 0. Now, in particular, we usually care about this. In the case of autonomous, or what are called autonomous differential equations. In other words, ones where you just have dy dx is equal to f of y. So in other words, an autonomous differential equation is one in which your variable x actually doesn't show up in the right-hand side. Your variable x or your variable time. In other words, your differential equation behaves, or your derivative behaves autonomously from the time variable itself, or from the independent variable itself. So those are the cases in which we usually care about finding critical points. And in those cases, as you can see, we only have to solve for the value of y. In other words, we're usually interested in finding what are the initial values that cause the solution to be completely flat. Okay, so to recap, we have an autonomous differential equation, dy dx, or dy dt perhaps, is equal to f of y. The critical points occur where f of y is equal to 0. And then we have this notion of stability. Now, in class, I had gone over two possible cases, but there is an extra thing that will be brought up on the homework set. It's not complicated at all. But here's the main idea. So, if solutions whose initial value is close to the critical point, approach it, as x goes to infinity, that critical point is called stable. If solutions whose initial value is close enough to the critical point diverge from it, as x approaches infinity, that critical point is called unstable. Now, the third case that they do ask about on the homework set, this is really not that much more complicated at all, is basically as follows. So if solutions whose initial value is close enough to the critical point, let's say diverge from it as x approaches infinity if the initial value is greater than the critical point, and approach it if the initial value is lesser, or vice versa. That crit point is what is called semi-stable. Okay, we're almost done going through the theoretical, the conceptual ideas here, and there's really just one question left to answer here. And that question is as follows. How can we tell whether a critical point is stable? And the answer is very straightforward. It is simply to look at the sign of the derivative in other words, f of y, just below and just above that critical point. If it is negative below, it is unstable below. If it is positive below, it is stable below. If it is negative above, it is stable above. If it is positive above, it is unstable above. If it is stable, both above and below, the critical point is stable. If it is unstable in both, then it is unstable. Oops. Unstable. And if it is stable in one, and unstable in the other, it's semi-stable. All right, so that's going to be the entire idea of the process here. All we need to do to find critical points and determine their stability is first to set that f of y. Again, we're assuming that we're just working with problems that are autonomous here. So the right-hand side of the differential equation needs to not have any x's or any t's, just the original function y in there. And so you just set that right-hand side, that f of y equal to 0, solve that, and you find the critical point. Then to determine the stability, you look at f of y and you check its sign, whether it's positive or negative, both just above and just below that critical point. If it's negative below, that means it's going down below, which means it's moving away. So it's unstable below. If it's positive below, that means it's coming up and approaching, meaning it's stable below. And the opposite is true of above. You need the flip. And of course, you then just look at what it's doing above and below, and depending on the combination, you either get stability, instability, or semi-stability. And that's the whole game, and it's not too difficult to actually apply this in practice. So now let's move on to the actual example problem I wanted to cover here, and this will be pretty short. I'm going to go over exercise 2.2.1 from the textbook. I believe one of the problems on your homework 4 is taken from this. And we are given dx dt. So this time x is the name of the original function, is equal to x minus 4. And again, note that there's no t's on the right-hand side, which means that we do have an autonomous equation. Now, on the homework set, I believe that this is going to be a multi-part problem that asks a bunch of different things. I'm not going to proceed through all of the exact steps as stated on the problem. I'm just going to show the work that you need to do to be able to answer all of those questions that are relevant to the material in this section. So first, find the critical point. Or critical points. So this is very simple. We set x minus 4 equal to 0 and solve. And this, of course, gives x equals 4 as the only critical point. Second, we want to check stability. So this is pretty straightforward. We're simply going to plug in, say, x equals 3 and say x equals 5. You want to plug in points that are just above and just below. If you had more than one critical point, you'd want to be plugging in points that are in between two consecutive critical points. But you don't need to plug in super close, just because you actually know once you've found the critical points that nothing too bizarre can happen in between them. So let's plug these in. Let's plug in x equals 3. When x equals 3, x minus 4 is equal to 3 minus 4 is equal to negative 1, which is less than 0. So this is negative. And when x is equal to 5, we have x minus 4 is equal to 5 minus 4, which is equal to 1, which is positive. And now there's a sort of a diagram that they, I think, ask you to identify correctly. I think they call it the phase diagram. It's nothing super fancy. It's actually just a sort of a graphical representation of what's going on here. And for the phase diagram, this is very straightforward, nothing too fancy going on here. You just draw the real number line. And this is for x. And you mark on this real number line all of the critical points. In this case, we only have one, which is at x equals 4. And what you do is that you then indicate with arrows, so I'm going to do this, say, in red, the direction that the differential equation, or that the solution moves both to the left and to the right of this point of x equals 4. Now we found that when x is equal to 3, the derivative was negative, meaning the function is decreasing. So on this side, we see that it is moving away. And when x is equal to 5, we saw that the derivative is positive, meaning that the function is increasing, moving away from 4. So we see that this is going to be the diagram. Very simple. You just put arrows on either side of each critical point. And then you can look at the arrows, and if both arrows are pointing away from your critical point, it's unstable. If they're both pointing towards it, it's stable. And if one is pointing towards it and the other one is pointing away from it, it is semi-stable. In this case, we can very clearly see that this critical point is unstable. That's really all that you need to do for checking stability here. Of course, some differential equations will be a little bit more complicated than just x minus 4, but the process is really just as simple. You just find the critical point by setting the right-hand side equal to 0 and solving, and then you plug in other values that are just above and just below all the critical points that you found to determine whether the derivative is negative or positive in each of those areas. You can draw the phase diagram just like this, not very difficult to do, and you just look at where the arrows are pointing to figure out if it's unstable or stable. Now, of course, I want to, at this point in time, point out that I believe on the homework set itself, they do also ask you to find the exact solution of the differential equation. And I'm not going to address that in this video, simply because solving this differential equation has really nothing to do with section 2.2, and it's entirely just uses tools from the first chapter, from chapter 1, and stuff that was already covered on the first exam. In this case, this guy is just separable. So this is not too difficult to solve. Just point out this guy's separable. So hopefully you should be able to do that on your own, and if you can't, I have a separate tutorial video that's already been made and posted covering how to solve those separable equations. The other thing I want to point out is that I believe the homework set does ask you to identify which of various different graphs might be the correct one for this equation, but if you have already all this information, you know whether the function is increasing or decreasing when you start either above or below the critical point. You should be able to identify the right graph just by piecing together this information. In this case, you'd have a flat line when your initial value is exactly 4. Everything above that is increasing, and everything below that should be decreasing. And that alone should let you find what the graph is. All right, that's about it for this problem. Again, these problems are pretty straightforward. There shouldn't be anything too difficult with these once you sort of know what you're trying to do and what you're trying to look for. But as usual, please let me know if there's any extra questions about this or anything that I haven't answered, and I will see you guys in class or in the next video. Bye-bye.